So let us do this. Let us first consider the mass fluxes involved. Okay. So this is the solid surface RS, and you can see that some mass flux comes in. Carbon mass flux is leaving the surface, and carbon dioxide is formed, and that also leaves the surface. But oxygen penetrates through this. Oxygen comes to the surface. So I write this. Okay. You can see the directions also, the flux. So m dot double dash C equal to the same direction, m dot double dash CO2 minus oxygen comes in opposite direction, m dot double dash O2. So this is at the surface RS. Okay, at any other R here, at any other R, okay, this is RS. At any other radius R, arbitrary radius, you can see that there is a net flow rate, which is nothing but the flow rate of CO2 at that point, and oxygen also is coming. Oxygen is always transported in this direction, the net flux. So again you can write the same thing, but please understand that there is no other consumption zone or reaction zones in the gas phase. So when you assume steady burning of this and there is no gas phase reactions, only one reaction is there, that is heterogeneous in nature, there is no gas phase reaction. So the mass flow rate of the species should be constant, because there is no like a consumption or production of any other species. So we can assume that. So in that case we can easily say that the net mass flow rate m net will be equal to the mass flow rate of the carbon. Okay. So that is the steady state condition. So what we have is, we have three species here, O2, N2 and CO2. If you try to write everything in terms of say carbon flow rate, then we need to solve only one equation, either taking into account of any one conservation. So that is what gas phase species. So we can write the flow rates of this these two species basically with respect to carbon by using this equation. Okay. So the reaction what we consider is again same global single step reaction, but this is a surface reaction here. 1 kg of carbon graphite plus S kg of O2 giving 1 plus S kgs of CO2, and the carbon burning rate is indicated by m dot C. Okay. Now we know from this equation the mass flow rate of CO2 will be equal to 1 plus S, the magnitude. Okay, magnitude of mass flow rate of CO2 will be equal to 1 plus S that of m dot C. Similarly, mass flow rate of O2, actually please understand that the flow rate of O2 is in the other direction, but the magnitude of this mass flow rate is magnitude is equal to S into m dot C. Okay. So now what I am trying to do is, I am trying to write the flow rates of O2 and CO2 in terms of the burning rate of the carbon itself. Obviously, the amount of carbon burned, that much oxygen would have diffused and that much CO2 would have formed. So we can easily write that by considering this reaction. While doing this, the benefit what we get is, one of the gas phase species is solved, that is enough for us. So let us take the carbon, the oxygen transport in the gas phase. So since oxygen is transported by both convection, that is net flow, and the diffusion, because of the participation of the oxygen in the surface reaction basically, and also note that the oxygen is coming towards the carbon like this. Okay, this is the carbon surface. Okay, so it is coming in the other direction. So the radial direction is like this. So it is coming to the opposite direction basically. So the inward direction, which is negative, that also you keep in mind. Okay, so let us write the Fick's law for this. The net mass flow rate of oxygen, net mass flux per unit area, so mass flux of oxygen will be equal to the net flow rate. Net flow rate is nothing but m dot C double dash, correct, into YO2 minus the diffusion of oxygen. Please understand this diffusion of oxygen, we have put the usual method is right, but diffusion is predominantly in the negative R direction, that you have to understand, because you can see that the O2, YO2 decreases in the negative R direction. Similarly, the DR also decreases in the direction. So this will be you have to note that the diffusion is predominantly in the negative R direction. The convection will be in the other direction. Okay, this m dot CO2 minus MO2, that is the net flow which is in the other direction, in the positive R direction. So this is the net flux. So now we can use this and appropriately take care of the negative positive signs. I write the conservation equation. So and also we can multiply the flux by the surface area of the carbon 4 pi r s square, then I get the mass flow rate itself. So you can see that negative. So m dot double dash O2 equal to minus S times m dot double dash C. So if you substitute it and multiply by this, I can write this net flux of the oxygen. The negative direction indicates that it is in the other direction. So obviously the profile indicates that. So that will be equal to, now I am writing this is nothing but m dot CO2, okay, minus m dot C. So this is the net flow rate basically into YO2 minus rho d 4 pi r square. You can put r or r square, that is not a problem. So this is the differential equation. So the first order differential equation for the mass fraction of oxygen can be written like this. And you know that this is a constant here, even though unknown, it is a constant. So we can solve this by applying the boundary conditions at the surface of the carbon, which is YO2 equal to YO2, yes, that is another unknown what we will have. We do not know that yet. Okay. So then see, you know this value YO2 infinity we know, okay, but YO2 at the surface we do not know. Similarly, the mass burning rate of the carbon, which is we are going to find, which is also not known. At as R tends to infinity, YO2 tends to YO2 infinity. So these are the boundary conditions which we will need, and we will integrate this and solve. So oxygen conservation equation is integrated, and using the boundary condition, the mass burning rate of the carbon is obtained. Okay. So the usual procedure what we have seen previously, the same thing we are trying to do here. So by separating the variables and integrating, I get and boundary condition one by one you have to apply. First you apply the boundary condition for the infinity, and next you apply the boundary condition for the surface. So you get the final equation like this. So you can see the separate variable m dot c is taken as constant, so taken away, dr by the term involving the radius, and also you see 4 pi and rho d are constants here. Similarly, the oxygen mass fraction taken on the other side, and it is integrated to get a expression like this. Now apply the boundary conditions and you get the final equation for m dot c involving the YO2 at the infinity and YO2 at the surface. So again a similar expression where 4 pi rs and the driving parameter rho d, because it is species conservation, the driving parameter for the mass is rho d, and natural logarithm of some term. So this obviously can be written as 1 plus b, which we will do later, correct. So again similar to what we got for the droplet combustion, we get a equation for this, but these are there is a unknown here. RC maybe is known, YO2 infinity is known, S is known. S is got by say 1 kg of carbon plus S kg of O2, S kg O2 giving 1 plus S kg CO2. From that we can calculate the S value. So S value can be got. So the unknown here is surface. What is the value of at the surface? Similarly, what the left hand side we have to find. So these are the two so the unknown has to be found. So how to do this? So again you can see the procedure is not very complicated, it is exactly similar as what we have done for the droplet combustion, and we got this. Again unknowns are there, nonlinear equations, profiles are nonlinear. We may have to include one more equation and solve it iteratively. Okay, now let us consider the surface kinetics. I have to produce one more equation. So for doing that, why I have to consider surface kinetics here is because we have already discussed that YO2 at the surface is dependent on surface reaction. So I need to consider something on kinetics, surface kinetics. So what we assume here is this equation, surface reaction C plus O2 giving CO2 is assumed to be first order. When I say it is first order, then it depends upon the oxygen concentration. Okay. So, the mass flow rate of the carbon, that is the burning rate, correct. So, this is kg per meter square second, this is mass flow rate of the carbon kg per meter square second, that will be written as some rate constant K C, some rate constant into molecular weight of carbon, okay, molecular weight of carbon, and this is the concentration of oxygen at the surface. So, now this is kilomole per meter cube, concentration of carbon. Okay. Now molecular weight is kg per kilomole, and this left hand side is kg per meter square second. Okay. So, this means the unit of Kc should be what? So, this kilomole cancels, so kg per meter cube, so it should be kg per meter square second. So, this will be meter per second. So, now it becomes kg, this cancels kg per meter square second. So, the unit of Kc will be meter per second. Okay. Now, as done for other rate coefficients, Kc also can be expressed in an organized form, where there is a pre-exponential factor A, then the activation energy EA, universal gas constant, and the surface temperature. So, we can do this and write the, so let us assume that the parameters A and EA are known. That can be anyway, we have to do experiments to determine the rate constant for the char oxidation or carbon oxidation. This CO plus O2 CO2, we have to again do experiments, isothermal experiments, varying the temperatures to in a range and try to extract the values of A and EA. And now let us assume that this is known to me. So, again now if you involve this, Ts becomes unknown. Again to calculate Ts, we have to invoke one more equation. Okay. Now Kc, I substitute here m dot C as Kc into concentration. I try to write in a different way here. That is nothing but what? Concentration is nothing but O2 at the surface is equal to molecular weight of the P by R Ts. Okay. So, this Ru divided by molecular weight of the mixture, and I am multiplying by molecular weight of O2 also. So, divided by. Okay. See, actually concentration is what? P V equal to N or UT. So, now we can see that concentration will be P equal to C or UT. So, using this we can find the concentration basically. So, concentration I have to get the mass fraction. So, I have to multiply by molecular weight of the mixture by molecular weight of O2. So, that is what. So, P by RUT will give you the concentration, correct. So, concentration written that, but I want mass fraction. So, when I want to convert the mass fraction, I have to involve mole fraction. So, when I convert that, I have to multiply by molecular weight of the mixture by molecular weight of O2. So, when I do this, I get this equation. Okay. It is again using this equation plus the mole fraction to mass fraction conversion, I get this. Okay. Now, this is known. Now, I try to write this m dot C, mass burning rate of the carbon, will be equal to 4 pi r square into m dot C s double dash. So, 4 pi r square into this term I multiply, I get this. Now, I call this as K suffix kinetics into YO2S, some kinetic parameter into YO2S. This kinetic parameter is nothing but this. Okay, this is the kinetic parameter I am talking about, and YO2S. So, this let us take as equation B. Equation A already is solved by oxygen conservation equation, species conservation equation. Then by taking into account of surface kinetics, I have created the equation B, which is like this, where the kinetic parameter Kc is involved. So, that is K kinetics, some coefficient involving kinetics into YO2S. Okay. Now under steady state condition, A and B should be the same. Okay. So the kinetic parameter depends upon pressure, temperature and particle radius. Okay, that is also known to me. Anyway, it will invoke another unknown, which is Ts. So that we have to solve again. But anyway, at the time being, we will let us assume Ts is known to me, then we will proceed. Now equation B is solved to get the value of mass fraction of oxygen at a particle surface and substitute in equation A. Okay, and again this is not very easy to do. When you try to solve this, non-linear things are there, try to solve this and put it back there and try to solve, you will get a very complicated equation, but anyway that is the only way to go about that. Or another method is to follow an electrical analogy. So we will write this equation B is written like this. So m dot C equal to coefficient, some coefficient of kinetics, k kinetics into YO2S, which we write as some difference. So YO2 divided by 1 by k kin. So this is the resistance R kin. So this 1 by k kinetics is called R kinetics. That is a resistance offered to the kinetics at the surface. So what is driving the combustion reaction is the gradient of this. Okay. So how fast this is consumed, the oxygen which is coming to the surface, how fast it is consumed. So this 0 I am just putting to indicate that if the kinetics is higher, it will consume fast. So this is like a delta y, the gradient divided by the resistance to that will be inverse of the coefficient of kinetics. So I can write this as equation C, and this is like one surface. See, for example, this is surface RS, and there is one. So this mass of carbon flows here, and here oxygen comes in, and this I call R kinetics, the rate at which the surface reaction takes place, so that this mass of carbon is burnt. So that this is one of the analogy what I make. So that based upon, see here surely YO2 equal to 0 at this point. Interior of the carbon YO2 is 0, but here at the surface it is YO2S. So the difference between these two is YO2S minus 0. That is like a potential, and the resistance which is offered is this organ, and this is nothing but the current flow. Like a current flow, the mass of the carbon flows out. So this is electrical analogy which we make. Normally in internal problems also we make this same analogy. Temperature difference taken as a voltage difference, and what are the factors that are affecting the this heat transfer, that will be taken as resistance, and the heat flow itself will be taken as current. So similar to that analogy, we are taking the difference in the mass fraction of the O2 as a driving force, and the resistance offered is nothing but it will be inversely proportional to the reaction rate. Correct. So K kinetics here you can see that is K kinetics is proportional to the reaction rate basically. So 1 by that it will be inversely proportional. So that will be resistance of the chemical kinetics. Okay. So that is one way to do. So I get one equation. Similarly, I can also work with the equation A, which we have got here by using the oxygen mass fraction conservation. Here you can see that some term here in the natural logarithm can be, as I told you, can be written in terms of 1 plus b, and we can define a b number. That is what I am trying to do here. So when I write that as 1 plus b, the b number comes to be like this: YO2 infinity minus YO2 surface. Again, that is the difference which is occurring in the gas phase now, correct? Now this occurs at the surface, and we are concentrating on the surface to the interior to get this equation, where the surface kinetics is important. Now when I say diffusion of gases and that oxygen basically in the gas phase, now I have to take the condition in the gas phase. So what are the resistance there to the gas phase, or what is the driving force in the gas phase diffusion for the oxygen, etc. Obviously this difference is called delta y here, and that will be the driving force for me, okay, for the oxygen to penetrate from the gas phase to the surface. Okay. Then the rate at which it is consumed at the surface is here, what we have described here. So, that resistance is R kin. The resistance offered to the diffusion I have to find now in the gas phase, that will be called R diffuse. So, that will tell you. So, you have to write this equation in a different way to get that. So, when now if I want to do this, I want to eliminate the natural logarithm. So, now I have written this log of 1 plus b, okay, and if b is very small, okay, what I can do? So, when I have log of 1 plus b, this can be expanded in a say Taylor series, and when b is small, the b square and higher order terms are dropped, correct. Then I can say ln of 1 plus b will be equal to approximately equal to b. So, that means that I will just put b here instead of 1 plus b, the simplification what I am trying to do. So, b is defined here. So, ln of 1 plus b is just written as b here, and now I can write, so keeping this as delta y, I can keep other terms here. So, that is what I am trying to do here. So, m dot c is some delta y here divided by other terms. So, s plus y o 2 s divided by 4 pi r s rho d. So, this term I call it the resistance offered to the diffusion, obviously because the diffusion coefficient comes to the bottom here, correct. So, this is resistance which is offered. So, diffusion is directly proportional to rho d. Now, in this term s plus y o 2 s divided by 4 pi s into rho d, the diffusion term, the rho d term comes in the denominator. So, this is taken as resistance offered to the diffusion. So, to the surface R s from the infinity, oxygen diffuses here. Okay, now one second, that is the resistance for this. So, here it will be O to infinity. So, this is again YO2S. So, this is the potential difference and this is R diff, this resistance is R diff. Okay. So, the amount of mass of O2 coming to the surface in the gas phase, from the gas phase to the surface is restricted by this R diffusion term, okay, R diffuse the resistance. So, we can write like this. So, this is going to restrict this. So, when I write this mass flow rate of carbon, we can write del y by R diff. So, the equation D is written for the gas phase diffusion, where the driving force is this delta y, YO2 infinity minus YO2S divided by the resistance which is offered. So, that is written by S plus YO2S divided by 4 pi R S rho d. Okay. So, we have this circuit now. So, you can see RS, and there is one resistance which I call R kinetic resistance. So, this will the mass flow rate, and there is another resistance here which is called R diffuse diffusion resistance for the mass flow rate of oxygen from the ambient towards this, and we can see this is the value of YO2S, and here say in this point YO2 equal to 0, and when you go to infinity, YO2 will reach a value of YO2 infinity. So, this is the electrical circuit we have. So, mass transport of oxygen, I put negative sign indicating that it is in the opposite direction to the radial coordinate or the mass flow of the carbon. Okay. So, now what is this? The entire here starting from YO to infinity, the mass fraction of oxygen goes to 0. So, that is the total delta Y. So, YO to infinity minus 0 divided by, there are two resistance connected in series here. One is the resistance offered to the diffusion in the gas phase, another one is the resistance offered to the chemical kinetics in the surface of the solid. So, when you add this, then they are in series. So, the net effective resistance offered is addition of these two, or kinetics plus or diffusion. So, this will be the total mass flow rate. So, this is the easiest way to do. Now, I have the values of R kinetics defined, I have the value of R diffusion. So, once you know this, I can solve. Anyway, you can see that if you want to calculate R diff again has the value of YO2S. So we have to have iterative solution only. Okay. See, R kinetics on the other hand, R kinetics is written with the kinetic parameter here. So you can see this k kinetic 1 by k kinetics. So it's 4 by r square kc and some molecular weights and p by ru ts etc. Again ts is unknown here anyway. Ts is assumed to be known in this analysis. Again we have to use energy equation to solve ts, that will be done later. So if we keep this, that is kc is known, everything is known, ts is assumed to be known. So k kinetics, so r kinetics can be solved, got. But R diffusion will involve YO2S and that should be again iteratively got. Okay. So I put the value of diffusion resistances here. You can see that the kinetic resistance and the diffusion resistance is S RU TS divided by 4 pi R square, molecular weight of the mixture. The K, this is the rate coefficient for the surface reaction into pressure. Okay. As I told you, surface temperature, reaction rate, surface radius and the pressure, everything dictates the resistance here, and it is inversely proportional. See, when the Kc is higher, reaction rate is higher, the resistance is low, pressure is higher, resistance is low, and so on. Okay. Here diffusion, again the rho d, and the rho d is higher, then the diffusion resistance will be low and so on. Okay. So this is the scenario here. So as I told you, RF involves the surface mass fraction of the oxygen, this term. So iteratively you have to solve it. So guess a value or do a combine the equation and do it as a this. So a quadratic equation can be generated and solved, or iterative procedure also can be used to solve. So there are techniques to solve this. Okay. Now before doing that, we can also try to eliminate the one of the resistance if one is very low in value compared to this. See, this is the equation I have. So YO2 infinity divided by the net effective resistance, which is the sum of these two. If one is very higher than the very much higher than the other, then I can neglect the other value, correct. So to analyze that, let us take the ratio of the resistances. The kinetic resistance to diffusion resistance is written like this. I have just factorized this. So S by S plus YO2S. Okay. Then RUTS by molecular weight of the mixture into pressure. Then diffusion coefficient. So rho d by Kc, rate of this, and the surface radius itself. So if you write like this, basically, actually this is there's a small typo here. Yeah, this 4 pi Rs only should come for the this resistance. 4 pi Rs only should come. So this R square should not be there. So it will be 4 pi Rs only. Okay. So if you take this into account, this there are scenarios. Let us say this ratio is much greater than 1, ratio is much less than 1, or it is almost equal to 1. We will get the modes of the combustion. So the combustion modes of carbon will be classified into 3 when the kinetic resistance is much lesser than the diffusion resistance. Okay. Kinetic resistance is much lesser than the diffusion resistance, then it is diffusion controlled, because kinetic resistance is very less. So kinetics is very fast. So what is controlling is the amount of oxygen which is reaching the surface, that is controlled by the diffusion. So that is going to control the entire process. So the process will be diffusion controlled, correct. So when the kinetic resistance is small, that indicates that the surface reactivity is very high, reactions are very high. So it will be finished and it is just waiting for the oxygen to come to the surface, and once the oxygen comes here, the reaction is completed instantaneously. So the diffusion of the oxygen towards the surface will control the combustion process. So this will occur when the RS is large, huge droplet, this particle diameter, or TS and P being high, you will get the diffusion control. On the other hand, so in that case, the resistance due to here, this is neglected, and you can write this without involving the resistance due to kinetics. Okay. The other extreme case is the other one, when the kinetic resistance is much higher than the diffusion resistance, then obviously the diffusion is faster here. So, the process is kinetically controlled. Oxygen is available, readily available. Once the oxygen is consumed, oxygen is instantaneously provided to the surface, but the chemical reaction takes some time to finish. So, it is kinetically controlled. So, this is the other extreme. Okay, when very small, the oxygen is present everywhere, very small droplet, the reaction takes some time to finish. Okay, oxygen is immediately will diffuse into this and wait, reaction is complete and so on. So, low Ts, low P and small Rs, this situation will be there. Again, only the kinetic resistance included in the equation. But in other cases where the resistance are not much different, or the ratio is 1, then it is controlled by both kinetic and diffusion. You have to use the entire equation like this. So, these are the mode. So, as I told you, Ts is unknown here.